Welcome to Electronline, and in this series we're going to talk about Markov's chains. It's a special section of probability and statistics, and it's actually a remarkable section. It's really interesting, and it gives us tremendous power in predicting what will happen in the future, depending upon what our current state is and what the probability of change will be. Let me explain. Let's say, for example, we have 3 stores in a small town: store A, store B, and store C. Let's say they're grocery stores. And on any given week, 200 people will go to store A, 120 people will go to store B, and 180 people will go to store C to do their grocery shopping for the week. But what happens, just like in any particular case, people don't typically go to the same store all the time. They may want to go to a different store because they like the sales better in that store the following week. So what will happen is, on a predictive scale, is that from store A, the customers, 80% of them will go back to store A the following week. For store C, 60% will go back the following week, and store B, 70% will go back the following week. In addition to that, for those people from store A that do not go back, 10% will end up going to store B, and 10% will end up going to store C. For store B, out of the 30% that do not stay in store B for the following week, 20% will go to store A, and 10% will go to store C. And of the 40% that do not remain in store C the following week, we can see that 10% will go to store A, and 30% of them will go to store B. If that's the case, what will be the number of customers in store A, B, and C the following week? And what will be the number of customers that will go to A, B, and C the week after that, and the week after that, and the week after that? If the probability like this stays the same, we can then predict over time what the customer base will be for each of the 3 stores. And eventually, they will converge to a particular number if the conditions remain the same. And that's the power of Markov chains. They will allow us to calculate what will happen the week after that, and the week after that, and the week after that, and we can see where things are going depending upon the probabilities. Now, when they change, we'll have to set up a new chain and then recalculate the predictive power of Markov chains. So over this video and the next videos to come, we're systematically going to show you how to use Markov chains. So here we're going to start simple. We're going to show you a simple introduction. So here we have the case where the way we calculate that is that we have a current state. The current state is that we have 200 going to A, 120 going to B, and 180 going to C. We then have the probability matrix, called the matrix of transition probabilities, that will then determine upon how we can predict how people will go to either the same store or different stores the following week. When we multiply that probability matrix with the current state matrix, we'll get the next state matrix. And we can do that over and over and over again to see where it converges to. So let's just do the one step right here. So here we can see that the probability matrix will develop that. Here we have the current state matrix, and we'll have the predictive state matrix. So we can say here that A1, A2, not A2, let's call it B1, and C1, that will be the next state matrix. That will be the number of people going to A, B, and C in the following week. Could be the following month, could be the following day, it doesn't really matter. So that's equal to the probability matrix. Now the probability matrix will have A, B, and C on the horizontal axis, and A, B, and C on the vertical axis. Those are just there for our benefit. And this is from 2. Now I know that there's 2 different ways in which they do these kind of Markov chains, and I'll show in a future video how other books and other institutions do that. So there's 2 different ways. Sometimes they have it from A to B like this, or they have it from A to B like this. They have the matrix kind of transposed, and we'll show you both examples. But let's start with this example right here. Then, of course, here we can do the current matrix. The current matrix of A, B, and C. We'll have A is equal to 200. We have B is equal to 120. And C is equal to 180. Now, typically, they don't leave the numbers like that. They make it such, they adjust it such that it's a percentage of the total. So when you add the 3 together, you get 200 plus 120 plus 180, that's 500, which means that 200 represents 40% or 0.4. B represents 0.24, and C represents 0.36. And notice when you add them all up, you get 1, the whole thing. So traditionally, they don't put the numbers down like this. They simply put the fraction of the whole down like that, and that will then be your current matrix. The probability matrix is simply converted percentages into numbers, decimal places. So from A to A is 80%. So from A to A, that's this cell right here, that would be 0.8. From A, let's say from B to A, so from B to A, that is 20%, that's 0.2. And from C to A, so from C to A, that's this one right here, that's 0.1, 0.1. So let's do that again, make sure we got that. So from A to A, you see that 0.8 or 80% stay from A to A. So this is from A to A, that's this cell right here. From B to A, that's 20%. So from B to A, that's 0.2. And from C to A, that's 0.1. So 0.1 is right here. Now we go from A to B. So from A to B is 0.1. From B to B, that's 0.7. And from C to B, from C to B is 0.3 or 30%. And then the third transition is from A to C. So from A to C is 0.1, 0.1. From B to C, so from B to C is 0.1. Finally, from C to C is 0.6. And there's your transition matrix, or your transition probability matrix, or matrix of transition probabilities. So this is really the best thing to call is this is the probability matrix that can predict what's going to happen in the future based upon what's happened currently and how we think things are going to change. Now let's go ahead and calculate this. So now we're going to multiply this matrix times this matrix to give us this matrix right here. So A1, A2, and AO, or A1, B1, and C1 are going to become, it'll be 0.8 times 0.4 plus 0.2 times 0.24 plus 0.1 times 0.36. So we're going to go ahead, we're going to go this way and multiply it times this way to get the first cell right here and add those up together. So this becomes, it'll be 0.8 times 0.4. So it's this cell times this cell plus this cell times this cell. So plus 0.2 times 0.24 plus this cell times this cell. That would be 0.1 times 0.36. And that will be the first cell right here. That will be our A value. Now where's my calculator? Right here. So 0.8 times 0.4 plus 0.2 times 0.24 plus 0.1 times 0.36 equals, and that's 0.040, 0.404. There we go. All right, next. Now we're going to take the second row, multiply times this column right here. So this becomes 0.1 times 0.4 plus 0.7 times 0.24 plus 0.3 times 0.36. Again, the way we do that is to multiply 0.1 times 0.4, 0.7 times 0.24, 0.3 times 0.36. So we go horizontally here and vertically there. So when we calculate that, we get 0.04 plus 0.7 times 0.24 plus 0.3 times 0.36 equals, and the next one is going to be 0.316. And finally, we're going to calculate by multiplying the third row times this column right here. So end up with 0.1 times 0.4 plus 0.1 times 0.24 plus 0.6 times 0.36. Again, it's this cell times this cell times this, and this cell times that. So let's see what that gives us. 0.04 plus 0.024 plus 0.6 times 0.36 equals, and this will be 0.298. Now, how do we know we did this correctly? When we add these three together, it should still add up to 1. So let's see if that does. So we have 0.298 plus 0.316 plus 0.404 equals, I get 1.018. I made a mistake somewhere. So 1.018 cannot be the correct answer. So that's how I know I made a mistake somewhere. So I need to go back and see if I did this correctly. All right, so let me recalculate the bottom one. So we get 0.04 plus 0.036 equals, it's 0.28. So there's where I made my mistake. So when I add them up together now, it's clearly that now it ends up to 1.000. So I have it correct. So it's an easy way to check at the end, make sure this comes up to the correct value. Now, if instead using the decimals, you had used these numbers right here, you could have done the whole matrix exactly the same way. And instead of getting decimals here, you would have gotten the number of customers in each case. Or you could simply say that I know that the total of all the customers is equal to 500. And so therefore we can say that if we want the number of customers, I multiply this times 500. And so I get 500 times 0.404. So I get 202 customers in this store, 0.316 times 500. I get 158 going to this store, and 280 times 500 divided by 1,000, I suppose. I get 140 going to this store. And again, when I add them all up, they better add up to 500. So now if I add this up, so I get 202 plus 158 plus 140, I get 500, so definitely that checks as well. So that's how we use Markov chains, at least the beginning of it. You can see that we have a current state which tells us what the number of customers are currently, or in a decimal state of the whole, how many there are in each store. This is how we think things are going to change over the 1 week, and then we'll end up with a new matrix representing the new state the following week. And all we have to do is multiply what we call the matrix of transition probabilities, simply the probability matrix, multiply times the current state matrix. That gives you the future state matrix. So this sometimes is also called the future state or the predicted state. All right, and that's how we do Markov chains. That's a good example. Of course, there's lots more videos to come to show you all kinds of things about Markov chains, how it continues, how it converges, and so forth. And I will also show you there's a different arrangement of how they write out the matrices. It's the same methodology, just the matrix is transposed. It looks a little different, but in essence, it's exactly the same. In the next video, I'll show you how to do the same thing, but using the different way of setting up the matrix. So stay tuned if you want to know about Markov chains.